Good afternoon, and welcome to hand-wavy chemistry, where we do not delight in the details, but rather bask in the big picture. Today, I want to talk about the shape of molecules and how we can estimate what the arrangements of bonds around an atom will be. The technique we will be using is known as valence shell electron pair repulsion theory, which sounds very intimidating, but if we break it down, it's not that hard to make sense of. Valence shell. Those are the outermost electrons around an atom. They're the electrons that are involved in bonding. Electron pair. Electrons, when they go into their subshells, pair up. We can have one spinning up and one spinning down, and then that shell is full, and we can think about a location for that orbital, for whereabouts those electrons are. And finally, repulsion theory. Electrons are negatively charged, so it makes sense that they would be repelled by each other. So our different electron pairs in the valence shell are being pushed away from each other. They want to spread out as much as possible. So when determining a molecule shape, the first thing we need to consider is how many areas of electron density there are. And then we can think about how to get them separated. For example, carbon dioxide has two areas of electron density, the carbon-oxygen double bonds. There's one on each side. So that's two areas of electron density. Now I could show you a 3D animation or a graphic, but that's not so useful if you're sitting in an exam having to think about what shape is a molecule. So I'll show you what I like to do when I need to think about the arrangement of bonds and electron density locations. And that is grab a few pens. These Sharpies represent the carbon-oxygen double bonds. They are the areas of electron density. My fist here, this will be our carbon atom. So we said there were two areas of electron density. Now, these are going to push on each other. They want to get away. So it's going to try to get away as much as it can until it reaches this location. Now they are as far apart as possible. If we move it any further, we start to get closer. If we move it this way, it starts to get closer. This arrangement is the most spread out we can get for two areas of electron density. And if you look at it, you can see it is linear. So with two areas of electron density, we are adopting a linear arrangement. Now, if we add in a third area of electron density, perhaps a boron molecule, or something like a ketone or an aldehyde, this is now going to start to push. You can see that there is a close 90-degree angle, but there's 180 around here. So things begin to move and spread around. And we end up with a trigonal planar geometry. 120 degrees between each of the areas of electron density. And we can keep doing this. If we add in a fourth area of electron density, for example, methane, we end up with a tetrahedron. If we add in a fifth, that one's going to go in this side, and we now have a trigonal bipyramidal geometry. And finally, if I add in a sixth area of electron density, we end up with an octahedron. You could fill in each of these 8 triangular faces to make a regular octahedron. However, what we have described so far is only about arranging the electron density, the areas where there are electrons. Electrons exist in bonds, but they also exist as lone pairs. For example, let's think about ammonia, NH3. There is a nitrogen atom attached to 3 hydrogen atoms through single bonds, so we have 3 single bonds, and we have 1 lone pair. That is 4 areas of electron density. Earlier, I said that with 4 areas of electron density, we should adopt a tetrahedral shape, and that is where we're going to start. So here we have our tetrahedron. We could have hydrogens down here, and we'll call this our lone pair. But lone pairs actually stay close to the atom that they are associated with. You can think of them as being short and stumpy areas of electron density. So let's just push that down so that only the cap is poking up. This is no longer a regular tetrahedron. The distance from here to here is now longer than the distance from here to here. Instead, it is a trigonal pyramid. So if we have 4 areas of electron density, but only 3 bonds, the molecule shape is that of a trigonal pyramid. So now let's think about water. Water has an oxygen with 2 single bonds attached to hydrogen, and it has 2 lone pairs. So water has 4 areas of electron density, but only 2 bonds, like so. So our lone pairs are short and stumpy. So we're not going to describe it as being a tetrahedron or a trigonal pyramid. Instead, we look at the bonds and we say, that shape is bent. Water has a bent geometry. And we can keep doing this exercise for molecules with more and more bonds. We said before with 5 bonds, trigonal bipyramidal. If we remove one of them, we now have a seesaw. If we remove 2 of them, we get a T-shaped molecule. And if we go up to an octahedral geometry, when we replace one of those bonds with a lone pair, we go to a square pyramid. And if we were to replace 2 of them with a lone pair, we would now have a square planar geometry. I've talked before about how you can determine if a bond is polar or nonpolar. Taking that information and combining it with the molecular shape is how you can determine if an overall molecule is polar or nonpolar. But that is a story for a future problem time episode. I hope you have enjoyed this video, and if you have, please make sure to like, subscribe, and share it with your friends. And if there's any topic you'd like to see covered in a future video, please put it down in the comment section below. Thank you, and I hope you have a wonderful rest of your day.